well, let me get screen sharing going and we will begin. All right, so let's just recall very briefly what forking and dividing were defined to be. So last time. So recall we say phi x a divides over a if there exists some sequence I, ai, I less than omega with with a0 equals a, indiscernible over a such that if I move my formula along tuples indexed by omega, by the elements of this indiscernible sequence, this is inconsistent. So this is dividing over a. Now, we defined a whole bunch of things, talking about forking, which is when you imply a finite disjunction of formulas that divide. We defined what it means for a type to divide or fork, which means that you imply a formula that does, and we define the independence relations. So let's just recall the definition very briefly of the independence relations. So we write A superscript D independent with B over A if and only if the type of A over A B does not divide over A. And then we had A forking independent with A over B if the type of A over AB does not fork over A. Okay, so you read the symbol as A is independent with B over capital A. And capital A at the bottom is referred to as the base. So this makes sense. And we have lots and lots and lots of examples. So which are worth thinking about. So last time we talked about the theory of an infinite set. And we described dividing in this case as just disjointness, i.e. A independent with B over C is equivalent to A intersect B being contained inside of C. So there's somehow disjoint over the base. Now, in the case of, say, a Q vector space, this just says that the span of A intersect the span of B is contained inside the span of C. So I should comment, like, for those of you that are not model theorists, you might try to guess what the language of vector spaces is, and you might guess incorrectly. So the question that you ask yourself for a vector space is, what is an element of a vector space? It is, of course, a vector. We don't think of the scalars as an element of the vector space. They're just part of the ambient field. I mean, they're just part of the ambient structure, but they're not elements of the underlying space. So the way that you encode a vector space in model theory is you have unary functions from the vector space to the vector space for each element of the field. And so the scalar multiplication is there as an operation, but the scalars are not elements of the structure. So a vector space, typically in model theory, is a abelian group which has these scalar multiplication functions as part of the language. So so it makes sense to talk about span, although given an n-tuple of vectors, its span is not a definable set. It's like a union of things that are definable from the thing. Okay, so then you have like algebraically closed fields. And here this just says A and B are algebraically independent. Over C, and that means that the transcendence degree of A over C plus the transcendence degree of B over C is equal to the transcendence degree of the compositum over C. So, or no, that's not what that means. So what it really means is, okay, I mean, what it really means is that the transcendence degree of AB over B is equal to the transcendence degree of A over C. So using B, you can't drop. You can't force the transcendence degree to drop. Okay. Okay. So
I have a
yeah,
question. With the Q vector space thing, what if A and B have elements in common that are not part of C, right?
great. Then you have forking, right? So the point is, suppose that I have some vector v in A, and v is in the span of B. Let's imagine that we have this situation, right? So what happens is we can write v as some linear combination, like alpha 1 b1 plus alpha 2 b2 plus dot 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 plus alpha n bn. And what we know is that the collection of b1 through bn is not contained in the span of C, because if it were, then we wouldn't violate this condition, right? So let's assume we're in this case. So pick bi, which is not in the span of C, and choose bij, pairwise linearly independent, such that okay, and let's say that this is minimal. Like I choose like a minimal collection of vectors which give me v. Okay, so pairwise linearly independent, such that the sequence bij, j less than omega, is span of C indiscernible. If it's not clear how to do that, just take an infinite collection of vectors which are linearly independent and then make them into an indiscernible sequence, like extract an indiscernible sequence using what we've done before. Although I think in this language, it's not so hard to check that if they are linearly independent, then they automatically are indiscernible. Okay, well then now just look at the equation. Consider the equation x is equal to the sum from I, or let's say k not equal to I, of alpha k bk plus alpha I b I j. So I'm varying these vectors bij, and everything else is held fixed. So what happens if you take a vector that satisfies two of these? Well, if you have a vector that satisfies two of these, then okay, so what are these linearly independent over? They should be linearly independent over, I guess, C and the rest. B not equal to I, something like that. I mean, this is certainly something you can do because it's minimal. Because it was minimal, you could assume these bi's are linearly independent. So in particular, I can choose these bij's to be linearly independent, not just over C, but over the remaining ones. Now, if you find a point in common between two of these equations, what do you obtain? You obtain a linear dependence between the bij's, and that's a contradiction. So in particular, this collection of formulas is too inconsistent, and that means it divides. Okay, does that make sense? So the idea is if you take a linear equation, then you can vary the coefficients in such a way that you obtain a too inconsistent collection of formulas. And this idea works also just as well for algebraically closed fields. If using B, you find a new algebraic relation, then what do you find? You find some polynomial which is satisfied by an element of A that's not satisfied by an element of C. Well, vary those coefficients. And if you vary those coefficients in an algebraically independent way, then you find that if there were a point in common to these different coefficients, to these different polynomials, you would find some algebraic relation that obtained between these different polynomials, which can't happen if you vary them in an algebraically independent family. So again, if you drop the transcendence degree, i.e. if you find a new algebraic relation, then that gives you an instance of dividing. And this is not such a different picture than what we saw last time, where we were looking at this equivalence relation. And we looked just at a pair AB, and we looked at the formula EXB. So EXB is a formula that somehow imposes relations upon A. And we can make that inconsistent by moving B in an independent way, meaning from one class to another. This sort of picture is the basic picture for simple theories, and the basic picture for NTP2 theories, and the basic picture for NSOP1 theories. If you have a dependence, then the way you can witness that is you can take some formula that witnesses the dependence and move it along a very independent sequence, and that should give rise to inconsistency. That should witness the dividing. Okay, so that's going to be something we explore quite a bit, how to witness the dividing. But at least these examples are like the standard examples that one should have in mind. You have something like disjointness, the simplest possible relation. You have something like this modular law that says that the intersection is contained in the base for span rather than just for set inclusion. And then you have this sort of algebraic relations that you see in algebraically closed fields. And these are going to be the three basic examples of stable theories that people think about.
Nick?
Yes.
So for the other ones, do we also need disjointness for
Yes.
the vector space? And
yeah, although I believe that's implied, right? So for example, if if A intersect B is no, okay. So here's a subtle point. Suppose that disjointness fails, but holds for the span. Meaning I can find two elements, A and B, which are not inside of C, and they're equal, but they're both contained in the span of C. Then what happens? Still, I don't have dividing. So the issue is something like, suppose I have C is equal to two linearly independent vectors, C1 and C2, and I have that A is equal to, I don't know, alpha 1 C1 plus alpha 2 C2, and that's also equal to B. Okay, so I claim that we still have A independent in the sense of the vector space, Q vector space, with B over C. And let's think about why. Well, suppose I take a indiscernible sequence starting with this element. If that's indiscernible over C, then what does it look like? It's constant, because C will say that if I take alpha 1 times the first thing plus alpha 2 times the second thing, then it's got to be equal to the element. And okay, that means that you have no choice. Once you look at the type of this element over C, it's completely determined. This element is definable over C. Because it's definable over C, then indiscernible sequences starting with it can't move. They're constant. And constant sequences can never witness dividing. So, well, okay, unless the formula is inconsistent. But that happens. But yeah, because constant sequences don't witness dividing in this case, you know that actually they're independent. So the correct statement is, okay, so correct general version of disjointness is that A, forking or dividing independent with B over C, it doesn't matter which, always implies that if I look at the model-theoretic algebraic closure of AC, and I intersect that with the model-theoretic algebraic closure of BC, that's contained in the model-theoretic algebraic closure of C. So you don't necessarily literally get disjointness because you don't see things that are algebraic or definable over the base just through disjointness. But once you replace the base with its algebraic closure and you replace the right and the left-hand side with their algebraic closure, then you do get disjointness. So it's a great question because this is an important point. By the way, this relation here is sometimes called algebraic independence, which is written like this. But it's confusing because this doesn't agree with algebraic independence in fields. So this relation is different than the relation of non-forking in fields. But that's also called algebraic independence. So there's often confusion. So I don't know that we'll talk about algebraic independence so much. Okay, so last time we talked about extension for non-forking. And today I want to give a collection of properties for the non-forking relation, which are sort of generally useful. We're going to build up a stock of these things. But the first proposition I want to give is one which is sometimes called the basic characterization of dividing. And it just tells you how to think about dividing independence. So the following three things are equivalent. Okay, so one of them is A is dividing independent with B over A. The second is for all indiscernible, or I should actually specify, for all A indiscernible, I, starting with B, with B0 equals B, I can switch A. So I can replace A with A prime, which has the same type over AB as A, such that I is A prime indiscernible. So I can upgrade the indiscernibility. I started with an indiscernible sequence, which was indiscernible over A, but by moving A to something else, I can make the sequence indiscernible over that new element, preserving the type over B. Okay, and then the third one is for all A indiscernible I, which starts with B, there is some I prime, which has the same type over AB as I, such that I prime is A indiscernible. Okay, so what does this one say? This says, you give me a sequence starting with B. If I know that A and B are independent, then I can move the sequence to something that has the same type over AB. So in particular, it starts with the same element. And now it's indiscernible not just over capital A, but over capital A and little a. So that says, again, you can upgrade the indiscernibility at the cost of moving the sequence by an automorphism. Okay, so this is really useful because if you ever want to prove anything about the dividing relation, normally you just play with indiscernible sequences in this way. So this is, I mean, it's not a deep or difficult thing, but it's super important. I mean, it's really the way you should think about dividing. So, I mean, when I work and all of my papers have used dividing in some way. When I think about dividing, I think about 2 and 3. I don't think about fixing a formula and making it inconsistent. I think about being able to upgrade indiscernibility. So this is, I mean, for a lot of things, this is the way you want to think about what dividing says. So let's pick a direction. So first thing, let's just quickly observe that 2 holds if and only if 3. So let's suppose we're given some I, which is bi I less than omega, with b0 equals b. So I'm going to draw a picture. So here's A, here's little a, and here's my sequence I, which starts with b0. Now, if we have a prime, which is the same type over AB as A, and I is a prime indiscernible, here we're going to use this model-theoretic fact that in a saturated model, if 2 things have the same type, there is an automorphism that takes one to another. So there is sigma, which is an automorphism of the monster model over AB, with sigma of A prime equal to A. So we had our A prime here, and we could find some automorphism that took me from here to here. Now, this automorphism takes I somewhere. And what we're going to call that new thing is I prime. And notice, because the automorphism sigma fixes AB, it fixes B0, because B0 and B were the same. So the starting point of this new sequence is the same, although the sequence itself is different. Then defining I prime to be sigma of I, we have I prime is sigma of A prime, A, indiscernible, i.e. it's A, indiscernible. Okay, so if you had A prime, which had the same type as A over AB, which has the property that I is A prime indiscernible, then you can move A prime back to A, and then that moves the indiscernible sequence somewhere. And the new indiscernible sequence, the image, is going to be indiscernible not over A prime A, but rather AA, by the choice of the automorphism. Okay, and for the other direction, it's the same thing. So on the other hand, if given I prime, which is the same type over A, B as I, let's call it I prime prime just to avoid confusion, such that I prime prime is A indiscernible, there is some tau in the automorphism group over AB with sending I prime prime to I. Anytime they have the same type, there's an automorphism taking one to another because the monster model is very homogeneous. Then defining A prime as equal to or I guess A prime prime is equal to, oh shoot, I switched from sigma to tau. So tau of A, we have I is A prime prime A indiscernible. Okay, so the point is I have to move something. Either I can move A and leave the sequence alone. So here we have our picture, right? Either I can move A to A prime, leaving the sequence alone, or I can move A prime to A and move the sequence. Or yeah, I can leave A alone and move the sequence. So I can either move the point or I can move the sequence. And it's equivalent to doing the same because I can choose automorphisms that do this switch for me. Okay, so 2 and 3 are equivalent by an easy automorphism argument. Let's go the other way. So now let's just pick one. Let's pick 2, and let's do 1 if and only if 2. So let's do 1 implies 2 first. So now suppose A is dividing independent over A with B, and I equals BI, I less than omega, is A indiscernible with B0 equals B. Then what we'll do is we will let Pxy be the type of AB over A. I'm just going to give this a name. First, we know, let's call this a claim. Claim. The union over I less than omega, Px Bi is consistent. Okay, why? Well, if not, then by compactness, there is some phi xy in Pxy such that if I take the union of the instances of phi where I'm moving phi along Bi, that's inconsistent. So phi x B0 divides over A, but that contradicts the choice of A and B to be dividing independent. A and B are dividing independent. That was an assumption, not a choice. It was an assumption. Okay, so this whole thing has to be consistent because if it were inconsistent, then it would give rise to a formula that divided, and we assume that there is no such. Great. So what we'll do is we will let A prime be a realization of Px Bi as I ranges over the natural numbers. Then by our Ramsey theory, or by indiscernible extraction, there is some I prime which is A prime indiscernible and realizes the EM type of I over A prime. This is something we did in great depth. But what we know is that bi a prime has the same type over A as bj a prime for all I and j. Why? Because A prime realizes this type, right? We took this type and we realized it with A prime. And that means that if I look at the type of Bi A prime or Bj A prime, these are always the same because the P was the complete type of that pair. So that complete type is determined. So all of the formulas in this complete type are in the EM type, right? I mean, what is the EM type? It tells me the things that are somehow universally true, no matter where I look in the sequence. So if I take a formula, which is, in the type of the pair Bi A prime, that's also going to be in Bj A prime. It's also going to be in Bk A prime, no matter which one I take. So it's got to be in the EM type. So if I label this I prime, let's call these Bi prime, I less than omega, I know also B prime I, A prime, has the same type over A as Bi, Bj, AI. So I mean, not only do they all have the same type with respect to AI, but they realize the types from before, which is the same as the type in particular of B0 A prime. So by an automorphism, let's say, can assume I prime satisfies B prime 0 equals B. Okay, what do I mean by this? So what did we do? We had A, we had our little A, and we had our given sequence. So this is the sequence that we started with, where this is B0, B1, B2, and so on and so forth. Then we found some A prime such that, like, if we looked at the complete type of the pair A, B0, we knew now that this A prime had that same complete type for every possible pairing with the sequence. And then using our Ramsey theory argument, we found another sequence, which is like B prime 0, B prime 1, B prime 2, so on and so forth. And that also had all of those same binary relations, all of the relations between B0 prime, B1 prime, B2 prime, so on and so forth. But the problem was that we wanted our sequence to start with B0. We wanted our sequence to have the same type as B0. So what do we have to do? Well, we know that by an automorphism, the type of B prime 0 over A prime is the same as the type of B0 over A prime. So I can move this and actually assume that my picture looks like this, because they have the same type. So it's just like before. There's some automorphism that takes B prime 0 to B0, fixing A prime. So I take that automorphism and I see where it sends my purple sequence, and that gives me my second purple sequence. Okay, so that's that direction. Now let's do the other one. So other direction, this one was 1 implies 2. So now we'll do 2 implies 1. This one is the easy direction. So suppose we know that if I is a indiscernible, there is, I should also say, starting with B, then there is A prime such that, and again, I'm not saying what satisfies A, B, A, such that I is a prime indiscernible then if phi xb is a formula in the type of A over AB, we know that A prime will realize the union of all of those formulas over the elements B prime as B prime ranges over the elements of I. Why? Well, we knew that the sequence starts with B0 and it's A prime indiscernible. And A prime has the same type over AB as A did. So if we have, okay, so Y, if we have phi A B, then that implies phi A prime B, because A prime has the same type over AB as A. And that implies phi A prime B prime for all B prime in I. Why? Well, because I is A prime indiscernible. So what's the conclusion? The conclusion is that phi x B prime as B prime ranges over the elements of I is consistent, since I and the formula phi x B in the type of A over AB are arbitrary. This shows A is dividing independent over A with B. What does it mean to divide? It means there's some formula in the type and some indiscernible sequence, such that if I move that formula along the indiscernible sequence, I get inconsistency. Now, we've taken an arbitrary formula and an arbitrary indiscernible sequence, and we showed that it was consistent. So that means it doesn't divide. Okay, so this gives us our basic characterization of dividing, which will be useful in understanding the various properties of dividing going forward. All right, so are there any questions about this? This is like a pretty fundamental fact about the way dividing works. Nope. Okay, so now what I would like to do are just catalog some very basic properties of forking. That are going to be always true. And then we'll start adding onto this list by assuming additional properties of the theory. So the first one that we did is extension. And this we proved last time, but I'm just going to repeat it so that it's fresh. So what this says is that if A is forking independent over AB, or sorry, over A with B, then given C, there exists some A prime, which is the same type over AB as A, such that A prime is forking independent over A, not just with B, but with C as well. Okay, so this we proved last time. And as you recall, this led to a certain compactness argument. If you take the negation of all the forking formulas, if that's inconsistent, then that meant that your type implied a finite disjunction of forking formulas. That means it implied a forking formula. That doesn't work with dividing, because if you take the negation of the dividing formulas, the compactness argument would tell you that your type implied a finite disjunction of dividing formulas. That's a forking formula, not a dividing formula. So forking exists to solve this problem, to make this compactness argument work. Okay, the next one that I want to say is base monotonicity. So what this says is if A is contained inside of B, then if you are independent over the small base, then you're independent over the big base. Now, what is the intuitive reading of this? The intuitive reading says, okay, what does it mean for A to be independent with BB over A? It means that using the parameters BB, I can't learn any new interesting information about A that capital A didn't already have. So if that's true, if all of the interesting information that A, capital B, and little b know about A is already contained in A, then it's certainly already contained in B because A is contained inside of B. You know, if moving from A to BB didn't give me new interesting information, then moving from capital B to little b also doesn't give me new interesting information. So that's sort of like the intuitive understanding of base monotonicity. So let me highlight that. Now, 3 is going to be one that looks kind of technical, but it'll turn out to be very important, which is called left transitivity. Okay, so what does left transitivity say? Left transitivity just says that if A is independent over A with B, let me change that to C, plus B is independent over AA with C, then this implies that AB is independent in the sense of forking with C. This looks technical, but for the moment, we'll just assume it as an axiom and then we'll make it seem natural later. Okay, so what is new? Last time we proved extension. Now we need to prove base monotonicity and left transitivity, and that'll be the day. So 1, we've done. So far, so good. Now we need to do 2. So 2 will be obvious for dividing. So clear for dividing. Since being B indiscernible implies being A indiscernible. So let's just think about it. What does it mean if I have a formula here that divides? So I'm thinking not about the F version, but the D version. So there's some formula in the type of A over A, B, B, and there's some A indiscernible sequence, which is inconsistent. Now, if I know that this thing fails, then what does that mean? It means that there's some formula in the type of A over BB, and some B indiscernible sequence that I can move it along, which gives me something inconsistent. Okay, that formula is also in the type of A over ABB, because A is contained in B. And that sequence that witnessed this inconsistency was B indiscernible. So in particular, it's A indiscernible. So that shows you that you divide over A as well. Okay, so for dividing, this is clear. And so clear also for forking. Because what is forking? Forking means that you imply a finite disjunction of formulas that divide. So if you have a finite disjunction of formulas that divide over B, each one of those formulas forks over A, or sorry, divides over A. So the finite disjunction that you implied was a finite disjunction of formulas that divide over A as well. So if you know it for dividing, then it just follows formally that it follows as well for forking. Okay, so base monotonicity is easy. Cool. So now let's do left transitivity. So left transitivity for dividing first. So what do we want to prove? We want to prove that if A is dividing independent over A with C, plus B is dividing over independent over AA with C, then that implies that A, B is dividing independent over A with C. So let's do the proof. So proof, if what happens, so if we're given I, which is going to be Ci, I less than omega, which is A indiscernible with C0 is equal to C, we know by, let's label these, let's call this 1, or no, that conflicts, let's call this A and B. We know by A, there exists some I prime, which is the same type over A C as I, such that I prime is A C indiscernible. Or sorry, A indiscernible, sorry. So let's draw a picture. We've got A here, we've got little a here, we've got little b here, and we've got some C and a sequence starting. So here's our I, and what we do is we move I to I prime, and I prime is now indiscernible not just over capital A, but over AA. So this thing here was A indiscernible. This thing here is now A indiscernible, using the basic characterization of dividing. Now, because I prime is A indiscernible, and B, recall B was that little b was independent with C over AA, there is I prime prime, which has the same type over AC as I prime, with I prime prime indiscernible over AB. So we showed, so now I moved it one more time. So this time I was moving over AC, this time I was moving over AC to I prime prime. This thing is now AB indiscernible. So we showed given any A indiscernible I, starting with C, there is I prime, which is the same type over AC. Let's say I prime prime, which is the same type over AC, with I prime prime AB indiscernible. By the basic characterization of dividing, we have AB is independent with C in the sense of dividing over A. Okay, so now we just have to take it to the hoop and prove it for forking. How are we going to do that? Well, this is really easy, in fact. So suppose we have A is forking independent over A with C. A is forking independent over, sorry, B is forking independent over AA with C. Then towards contradiction, assume that, oops, AB is not forking independent over A with C. So there is some phi xy C, in the type of AB over AC that forks. So what does that mean? That means phi x c implies some finite disjunction of I less than k, psi x d. So d is some collection of tuples, some tuple that we don't see in the base. So by extension, we can find where each of these, I should say that each divides over what? Over A. Sorry. So by extension, we can find A prime, which has the same type over AC as A, such that A prime is forking independent over C and D. Then we can find B prime such that B prime has the same type. So if I look at AC, I can find B prime such that ACB is the same type as ACB prime, because AC certainly has the same type as AC, and well, this is the same thing as finding B with the same type over AAC, and that's certainly possible. So we have A is independent in the sense of non-forking over A prime is independent with C, plus B prime now is independent over A prime with C. Oh, sorry. I wanted to say A prime here. And this is possible. I mean, okay, so this is unclear, but really what I mean is like over AC, because this is possible because A and A prime have the same type over AC. So this follows just because, these things are conjugate by an anamorphism, they have the same type. But I know that this implies the stronger property, the weaker property of being dividing independent. This implies the, D, gosh. Sorry, okay, no, I shouldn't have tried to rush. So okay, I'm gonna apply extension here to also get D. So also by extension. Okay, so then we have B prime is independent over CD with A prime in the sense of dividing, because non-forking implies non-dividing. But if I knew that AB forked over A with C, we get that this implies, and here it's worth reflecting on why this is true, that it's not dividing independent with CD over A. Why? Well, what did we know about the type of AB over C? It implied this finite disjunction here. And the parameters for that disjunction were these D. So if I add those parameters to my type, the type has to pick one of the disjuncts. Like the type can't say, I'm not in this disjunct, 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 because the type contains the formula phi xc. But now because the D's are in the parameters, it has to say which disjunct it picks, because that's something that the type knows about. So it has to pick one of the disjuncts, which means that it actually proves a dividing formula. So I have this, but I have this, and that contradicts left transitivity of dividing, not for forking, but for dividing. And that's something we proved at the beginning. So this is a contradiction. So once you know extension, left transitivity of forking follows from left transitivity of dividing, and that concludes the proof. So I went way over. I'm really sorry. I won't do that again, but I really wanted to finish this. So So next time what we'll do is we'll actually start imposing the assumption of simplicity, and we will see the consequences. Once you have some combinatorial assumption on the theory, there are lots more that you can say about forking. Okay, are there any questions?